All right, hello everyone. So as introduced, this work is done by Simon Doge and myself, John Gaspo. All right, so in this work we'll be interested in code-based masking. Basically, code-based masking generalizes many existing schemes. So if you have this sharing Z, and you have a set of sensitive variable x and a set of random variable y, you'll do the computation of x times g plus y times h, where g and h are two generator matrices of the code word C and D. We say that it generalizes many masking schemes because depending on how you define these matrices, then you can restrict it to be another masking schemes. Like if you define this matrix H to be of like this column of value of 1, and then the identity matrix, this is what will give you a Boolean masking. If you then change this first column to be now this public values, now you get inner product masking. And if you get free of those restrictions, you go to code-based masking. So again, we distinguish the word level security and the bit level security. So we say that on the word level security, we allow a probe to reveal a full element in the field, so a whole share. And this can be evaluated in the, under the standard probing model. So it's just the number of shares minus 1 as usual. Now, if we go to our final level of security, we go to this bit level security. We allow probe to now reveal a single bit. And now basically, this has been connected to the dual distance of the code word D minus 1. And basically, the security in the bit probing model implies security in the bounded moment model with the same order. And this is typically what you evaluate during TVLA. And obviously, the word level security cannot be higher than the bit level security. So code-based masking has some nice benefits, especially for software masking. But one of it is that it achieves higher bit level security compared to Boolean masking with the same number of shares. So we have this kind of security order amplification effect. And with code-based masking, since you have more flexibility on the generator matrix G and H, then you can amplify this dual distance so you can have increased or the optimal amplification. So you see that for a 2-share, and then you have 4-bit element, you already reach a third order security compared to the whole level, which will always be stuck to n-1. Same as Boolean masking will always have the bit level and the word level security to be equal. So that's something you would like to have. But there are limitations with the existing code-based mask gadget. Well, the first one is that it is kind of difficult to maintain this bit probing security during secure computation. And well, it has a larger overhead compared to Boolean masking. The first reason, it's obvious because you're using a more algebraically complex encoding function, so you have some kind of overhead. And then another reason is that it's at the moment not possible to apply the bit slice optimization. And with Boolean masking, you often like to use bit slice optimization. And also the existing mask gadget, they're defined to work over word element. So this is why it's only used with cipher whose hashbox can be efficiently computed with a power function over the word. This is why you often see like paper on IPM or code base that are using AES, just because the inverse or the S-box can be efficiently done. But as a result, you have no mass cipher with the bit level S-boxes that have been implemented with IPM code base. So what we do in this work is that we introduce a series of gadgets over code-based masking. Basically, we mainly define this thoughtfully gadget, which is a nonlinear gadget. And out of that gadget, we derive a linear add gadget. And out of that, we derive a swap gadget. Now we demonstrate the composability with the T-Piney security at the bit level of each gadget. And we show how we can make full ciphers using the gates that we define. So just for the linear layer, you can have a combination of add and swap gadget. For the nonlinear layer, it's a combination of add and the Toffoli gadget. So I'll spend most of my time explaining this Toffoli gate gadget because it's how everything is made, and then the rest is derived from that. So the Toffoli gate, as you can see over there, it's a simple nonlinear gate that takes some set of input bits, and then it will make some nonlinear operation on that. So it will always, as output, give the same set of input like ABC, but then add some multiplication of 2 of the input bits. So here it maps C to C plus AB. what we do in our work is basically we make a mask version of the extended Toffoli gate. So now we basically allow to have two sets of inputs. Here you have ABC and EFG, and basically now the output is always all the bits from the first input plus some multiplication of bits in the second set. So here we can multiply EG and add it to C. So the gadget that you see here, basically it takes the two shares. Those are the two sets here. They're shared, X and Y. And then we have some indices that are used to define what we want to multiply together and where do we want to add this result. So basically the bits, the value V and W, they're used to define, okay, I want to multiply the secret bit from YV with YW. And where do we want to add that? Well, you add that to the bit at index U from the output. So the gadget works in three parts. In the first part, we duplicate and refresh the input share Y. This because we're making a multiplication, so we need to have the two inputs to be independent. For that, we use some kind of zero share gadget that we call code base zero. If you attended the presentation that I did a little bit before, it's a little bit the same concept, but now with code based. So once we have refreshed, basically we go to part two. Here we have this, we define some set of binary shares. Basically we call them SV and SW. So each of those sets, they contain the t+1 indices of binary element whose XOR will unmask either as YV or YW. Basically, we use this set to be able to make then this multiplication of the elements using the binary shares. And that's what we do in the part 3. Once we have this set of indices, basically, we make the binary cross product and we do, again, some kind of refreshing. I'll make an example with just for the beginning with the masking. So we use this to generate our matrices with the matrix H, having this property that then gives you this third bit level security. So you see that now each bit of the secret, like the bit A, is masked with like 3 bits of the random value x1. Now for the Toffoli gate example, let's assume you want to do with parameters u3, v0, and w2. So that means we want to take the bit and index 0 and 2 from y, so e and g, multiply them together, and then add them at the index 3. So you want to have d plus eg. So first what we do is that we refresh this share of y with the code base 0 gadget. We obtain this refresh value. Now basically we get this set of indices. So now what I mentioned with this SV set is basically tells you, okay, if you want to unmask or get the bit secret value E, you'll need to fetch the value E0, F1, G1, and H1, right? So once we have that, we'll be able to make the cross product. So we make this binary cross product, and we again will use some of those code base 0 gadget. So we want to make E times G. Basically, you have to make these 16 cross product values. I'll just explain how you make one of those cross products, and then basically you iterate that process. So first you generate a secure encoding of 0, so you get this code base 0 gadget calling. It gives you some sharing of a value 0. We call alpha, beta, gamma, delta. Now at the moment, the output is just, for the moment, just the shares of the first input, so A, B, C, D, right? Then basically you do the cross product, E0 times G0 prime, and you add this the bit index U of this R0 value. So you take the delta 0 share 0, you add it to this cross product. Then in the next cycle, basically, all the remaining bit of this randomness are placed to the output except the one at index U. And in another case, cycle, then you add this remask cross product. So if you iterate all this process, now 16 times, basically what you get is that at the index 3, basically you get the unmask E times G. And basically all the rest are some sum of sharing of 0. So basically when you do the decoding, and this sum up to some 0 value multiple times. So then you decode and you get the expected value that we wanted in the example, which is D plus EG. So we wanted to apply that now to a full cipher. We picked Skinny. Skinny is a tweakable block cipher, so it works over 6428-bit blocks. It has a tweaky size scalar with its block size, and it runs over 32 rounds. We picked it because it's intended for efficient hardware and software implementations. We'll do a software implementation. All right, so I presented this general algorithm. You can do any cipher with that, with this Toffoli gate and so on. But you saw that we had to call this code-based zero gadget multiple times. So again, you have this kind of high cost of randomness and construction cost. So what we wanted to do is to design an efficient tailored implementation. So we went for a bit slice implementation to be with 2 shares, but third order secure. Again, we picked this matrix G and H, as you see before, and as in the example before. We went for an implementation for Cortex M4. And we did the implementation purely in assembly because well, we don't trust the compiler. And basically, we want to have complete control over their register usage. So the Skinny S-box is basically a 4-bit S-box, and we follow the construction from Shamir Sadi et al., which basically is made by a combination of affine function. So it's just pretty simple. It's just some bit swapping or just adding some value 1 here and there. And then 2 times the same quadratic class, which is the Q294. And basically, this quadratic class makes this mapping from A, B, C, D to A plus B, D plus, and then B plus C, D. So it's like this 2-time call of the Toffoli gadget. So we thought about some optimization on the computation of this quadratic function. Basically, you have to compute B times D and C times D. And so because we were in code-based masking, we have these 2 matrices. What happened is that in the masking of B and in the masking of C, you are reusing or sharing these 2 randomness values, so A1 and D1. So basically, if you make these 2 consecutive calls, basically you can reduce that kind of this cross product because you make them twice. So the idea is to compute only once and then reuse this. So you can save 8 cross product that you do this A1 plus D1 times D, and then reuse it for both. That's a nice optimization, but then you need to be really precise on the order of how you do this whole quadratic function, because otherwise you might lose the security. So basically, we do that, and then we show that it's Piney secure. We did the formal verification, and then we went for a custom script to iterate over all the cases and to verify it is Piney secure. Looking at the algorithm efficiency with our optimized Q294 quadratic class, we compared that with Boolean masking using ISW for the multiplication. So you're doing 2 times this multiplication, so it's 2 times 6 the randomness, so 12 random bits required. You have the 32 AND gates, 56 XOR, and basically with our optimized, you save this 8 AND computation, so you have this 24 for our case, and then we managed to squeeze a bit the number of randomness up to 9 bits. Now, if you would use the general algorithm that we used, that I presented before, then that will blow up, especially in the number of randomness and XOR. So a few remarks on microarchitectural leakage in software is often quite a problem. So the thing is, the nice thing with IPM and codebase is that it helps you with transition leakage, at least with word element, just because if you have this Hamming distance between like these 2 shares, with Boolean masking it leaks directly. But with code-based masking with appropriate values, then it remains uniformly distributed. So you're safe with that. But if you look at the bit level, you can still have issues. And for that, for example, you can look at what you see on the right, basically, because we had a bit slice implementation, so all the bits are independently, the first bit is register 0, and so on and so on. What happened and what did happen during the test is that you might have, for whatever reason, a transition leakage between A0 and B0, and then if you have another transition leakage in A1, B1, in your trace, when you do the bivariate evaluation, then boom, it leaks. So we reuse some algorithmic property that we defined in another paper, which was about some vertical non-completeness, horizontal non-completeness, and register uniformity, where basically it states that now each of the shares, they have to be shifted by a unique value, right? So this is the bit slice data representation. So in the register R1, basically you have all the first bit of the first share, and then so on and so on. Normally, everything will be aligned. That creates the risk of like transition leakage. We shift everything by a unique value. We check the cost and cycle count. So basically what we wanted to evaluate is our code base implementation for 2 shares comparing with Boolean masking of Skinny. So we compare with 2 share Boolean masking Skinny, which is first order secure, and then a Boolean masking of Skinny that is with 4 shares, so with the same level of security than ours. And what we observe is that with our implementation that only use 2 shares, we can be 1.4 times faster, and we use 25% less bit of randomness. We did practical leakage detection, so we went for 1 round of Skinny. First order doesn't leak, that's nice. And then we went to evaluate the second order bivariate. Again, this doesn't leak, and then we went for the third order 3 variate. So the thing is, the higher order you do, the number blows up in terms of point that you need to evaluate. So the thing is, for the 3 variate case, we had to downsample and reduce to the Skinny S box only. All right, that concludes my talk with the, we basically introduced mask linear and nonlinear gadgets that preserve this bit level T-Piney security. We demonstrate how we can make cipher from that, and we made a tailored 2-share third-order bit-slice Skinny implementation that is equally secure than Boolean masking, and we use faster, we are faster and we use less number of random bits. We made formal proof and practical leakage detection for 1 million trace with no leakage. And the code is available online if you want to have a look at it or use it. And that's it. So thank you for your time.
Thank you, John. Do you have any question from the audience? Some déjà vu.
Are you aware of the fixed sliced representation of Skinny?
No.
Okay. that takes away my question.
To maintain the security order amplification you get from the bit probing security, you need to have linear leakages, right?
Yes.
And have you encountered cases when you were doing implementation where this was not true, like having quadratic leakage or something, and that broke everything down, or you never had that? This
no,
happen?
I think the thing is that when we implemented it a few times, we had leakages, and then we went to like trial and test, and we passed to pro lead to detect where it was leakage and so on. But most of the time was related to like. At the beginning, we were not doing this shifting thing, so we had transition leakage that will impact, and we were not reaching second order secure, whereas it should be third order, but otherwise, not really, yeah.
Yeah, you only did on the Cortex M4, right?
Yes, only on the Cortex M4, yeah.
Well, then, yeah. I guess it should be linear.
Any other question? Well, I have 1 or 2 questions, if you may. First of all, so you showed here the Piney security. Whereas in your previous talk you showed the SNI security on your inner product masking. Is there any reason why you choose one security notion for this kind of masking scheme or not?
Yeah, so the thing is, for the first work that I presented, we use SNI because I was looking at Joseph Balach work on IPM, and they were doing like proof with TSNI. So I was like, okay, we'll go with SNI. The thing is, like with SNI, you need to have this refresh gadget and so on. So when we went for this work, we thought, okay, we'll do it Piney, and that will make it more elegant for like composability and so on. Okay,
but do you think that this security notion, the Piney security notion you proved here, could also apply to inner product masking? I guess because it's a particular case. And inversely, do you think that you could prove SNE security on code-based masking?
So for this to be SNI, I think we can have, because whatever we get from the output, we can simulate it with nothing. So we kind of get that. And for the other one to go to Piney, I wouldn't know.
Future work?
Future work then.
Okay. Well, let's thank the speaker again. Thank you, John.
Thank you.
And next talk will be given by Kitian about some instruction set for masking.
Good afternoon, everyone. I'm Qi Tian from Shandong University in China. It is my great honor to be here to introduce our work. The title of my presentation is a code-based ISE to protect Boolean masking in software. And my talk has 4 parts. First, background. Side-channel attack can indirectly obtain sensitive data by analyzing the physical information generated during device operation, such as power consumption, timing, and electromagnetic. And power and electromagnetic attacks are the most common types. And with the wide use of embedded devices, attackers can easily get these devices. So, in this case, side-channel attack poses a significant threat to data security in embedded environments. Masking can resist the side-channel attack by introducing random numbers to obscure the side-channel information generated during the processing of sensitive data. And Boolean masking, as a simple and popular masking technique, is widely used to protect cryptographic algorithm implementations. It can split the sensitive data into some random and independent shares. For example, it can randomly encode sensitive data X into the order share consisting of D+1 shares. However, there are some challenges in software implementation of Boolean masking. First, in terms of efficiency, Boolean masking requires a lot of random numbers, and it also has a high computation and storage cost. Second, in terms of security, the low-noise environment of processors can reduce the protection of Boolean masking, making it easier to suffer from some attacks, for example, horizontal attacks. In addition, there is transitional leakage, which is caused by the leakage of some storage units, such as registers and memory, during state transition. Typical examples includes register overwrite leakage. And the red figure shows the t-test analysis of the first-order ISW multiplication on the IBEX. So it is important to prevent transitional leakage and increase noise level. Next, design and implementation. Code-based masking has advantages in resisting side-channel attack. Its more complex algebraic structure makes it more robust in transitional leakage, and it can reduce information leakage under low noise conditions. As shown in the figure, code-based masking can encode m-bit secret X into an n-bit sharing, where each bit is a share, and here A is an invertible matrix, and R is an n-m-bit random number. We first use Boolean masking to encode secret X into some random and independent shares, and then we use code-based masking to remark Boolean masking in order to protect Boolean shares. For example, a Boolean share XD can be encoded into a code-based share X hard D, and we call X hard D a protected Boolean share. And in our design, m equals 16 and n equals 32. By operating on the protected Boolean masking instead of the original shares, we can prevent transitional leakage and increase noise level. This figure shows a simple view of connections between components in the processor. we assume X hat and Y hat are two protected Boolean shares, and our goal is to compute Z hat equals X hat, X or Y hat. First, X hat and Y hat are decoded to get their unprotected Boolean shares, and then the ALU computes result, and finally, result is decoded to get Z hat. The decoders are only activated when our custom instruction is executed, while encoder is optional. In addition, we use the PRG to produce random numbers. Before final encoding, we can optionally XOR the ALU result with a random number to refresh the randomness of Z hat. For the PRG, we use a leakage resilient PRG as shown in the figure. The permutation function P is executed once in each clock cycle to update the inner state S. And this PRG has an important property. Even if attacker gets multiple outputs and some leakage information, the next execution can still generate a random number. And more security proof of this PRG can be found in the appendix C of our paper. Then, instruction design. Our IC supports some different operations on code-based masking in two ways. First, we provide a set of computation instructions, including AND, OR, XOR, SLL, and SRL. As shown in the figure, all these instructions have the same prefix CBM, short for code-based masking, and we use both R-type and I-type to implement them. The decoders are used by default, while the encoder is optional, controlled by the habit of the ES field in instruction encoding. And similarly, whether the ALU result is XORed with a random number is also optional, controlled by the low bit of the ES field. And we can use some instructions like CBM XOR to encode unprotected Boolean shares into protected ones, or decode protected Boolean shares into unprotected ones. In addition, we can use instruction XOR we can use instruction XOR instead of CBM XOR in some cases. Second, we provide 3 instructions to manage the PRG. The permutation function P is kcheck P100, and the instruction CBM PRG is used to control the PRG state. It can reset the PRG with the current seed, manually generate a random number, or decide whether to generate random numbers automatically. The instruction CBM S2R moves a random number from PRG to a GPR, and the CBM R2S does the opposite. Then, in our security proof, we assume 3 requirements. Requirement 1 and requirement 3 are for hardware, and requirement 2 is for software. If the implementation of hardware and software can fulfill all these instructions, all these requirements, it can prevent transitional leakage and increase noise level. First, requirement 1. For each gate in the circuits between GPR and decoder, at most one input can depend on a bit from resistors. This can be satisfied by using resistor gating. And then, requirement 2A, related sensitive data must not be accessed within 2 consecutive instructions. This is for formal verification. And for practical use, only requirement 2B is needed. related sensitive data must not be accessed within two consecutive CBM instructions. This can be satisfied by using XOR instead of CBM XOR, or by inserting NOP instructions and so on. Finally, requirement 3. The SNR of combinational secrets should be lower than that of registers and memory. This is true for most circuits. Then implementation details. We implement our design on the IBEX, and we use IBEX demo system as the SOC, and the base ISA is RV32 IMAC. As shown in the figure, our implementation uses two decoders, one encoder and 4 demultiplexers, 4 multiplexers, and one PRG module. For decoder and encoder matrix, we use a matrix whose inverse is itself, and the implementation of matrix multiplication can be regarded as the shortest linear program. We provide two versions of implementation, error-optimized and frequency-optimized. The error-optimized version requires 182 XOR operations, and its frequency is 289 MHz. And the frequency-optimized version requires 251 XOR options, and its frequency is 340 MHz. In addition, we use register gating. It can address the problems of wire switching on intended reads and glitchy signals by placing an AND gate after each register. Next, evaluation. We first test the hardware overhead and frequency for two versions. In optimized version, the register LUT and GE increased by 7%, 21%, and 8%. The FPGA frequency and ASIC frequency dropped to 87% and 83%. In frequency optimized version, the register LUT and GE increased by 7%, 23%, and 10%. The FPGA frequency and ASIC frequency dropped to 89% and 98%. Then, we use COCO as the formal verification tool to test the first order ISW multiplication. On the hardware side, it fulfills requirement 1 and requirement 3. And for the software side, it fulfills requirement 2A. The test result shows that when using RV32I instructions, leakage can be detected, but when using our CBM instructions, no leakage is detected. Then we perform security evaluation for error-optimized version using CW3205 and CW Lite with the processor running at 8 MHz. The software fulfills requirement 2B. First, to verify our design can address the transitional leakage in registers, we use the MV instruction to overwrite Y hat and X hat, and carry out t-test analysis. The numbers of traces used for t-test analysis is 10 million. As shown in the figure, when using our CBM instructions, all t-test values remain below 4.5. Then, we test the first order ISW multiplication. The number of traces used for t-test analysis is also 10 million. In addition, we perform SNR and MI analysis on a share based on 300,000 traces. The result is consistently good. Finally, we test the first order bit-sliced ASS box implementation. The result is also good. Next, future works. First, we could increase computational capacity. In our current design, the capacity is limited to 16-bit. One possible approach is to use a masked storage in a CSR to dynamically control the computational capacity. Then it is interesting to introduce photo detection, which is for code-based masking. For example, we can divide the original 16-bit random number R into a fixed 8-bit constant of all ones and 8-bit random number before encoding. During execution, if the decoded high 8 bits are not all ones, the interrupt program will be executed. Finally, we could apply the IC to other errors, for example, some masked implementations of algorithms such as Kyber and Dilithium. That's all. Thank you for your attention.
Thank you. Any question? Okay, let me start with the first question. So in the future works you mentioned, you said that you would like to implement your ISC to Kyber or Dilithium. Have you ever considered starting with maybe less ambitious algorithm like AES?
Yes.
A smaller algorithm? Not yet?
Can you speak more slowly?
Sorry. Have you implemented your ISC to AES or symmetric crypto, for example? Okay. This is AES S-Box. Okay.
Yeah.
And did you implement the whole AES, the complete?
No, we just tested the first order ASOS box.
Okay. Any other question?
Nice talk, thanks. If I understood correctly, you did not implement arithmetic functions like addition and multiplication, but it should be possible, or?
Can you speak more slowly?
I understood you only implemented securely the logical functions, not addition, not multiplication, correct?
We don't implement the function of for addition and multiplication. So if we want to apply the ICE to some algorithm like Kyber and Dilithium, we need to add some new instructions like for addition and multiplication, and so on. And the difficulty is that we need to model a prime number.
The prime numbers, sorry? You needed to model what?
We need to model a prime number.
Okay, thank you.
Any other question? May I finish with one last question, please? In your slide number 9, so you mentioned your idea of first splitting into Boolean shares and then encoding according to code-based masking.
Yeah.
Why not just directly encode your secret directly in code-based masking?
this we have how to say we have performed some evaluation. If just use code-based masking to encode secret X, it's not enough. And other masking techniques are required.
Okay. Any other question? Well, we can thank the speaker again. Thank you.